highly active group. Yeah, he has got a very highly active group, like 2 postdocs and 12 PhD students, as well as bachelor, master, and diploma students. And in fact, some of my students see his students at conferences every now and then. So it's very nice to have him here in person and to have him talk about his work. So his research pursues quantum mechanics for both, teaching as well as for fundamental research. He investigates the properties of individual quantum systems, such as single atoms, photons, or optically active impurities in solids and ultracold quantum gases. This is of very fundamental interest because it touches on the transition between classical physics and quantum mechanics, and also from individual quantum systems to many-body systems. And he has got an amazing breadth of research. Like he takes individual tracer atoms in ultracold quantum gases. He has done some work on quantum heat engines, on Bose gases in dynamic disorder, on the fusion dynamics of individual atoms through laser fields or through disorder potentials, and also on NV centers, for example, the development of fiber-based endoscopic NV-based sensors for magnetic field measurement. And he's also part of the WiMAX-1 quantum computing effort in Germany, where they work together with the University of Hamburg and the Fraunhofer Institute to build a practical quantum computer. So we're very happy to have him here, and he's going to tell us about some of the advances in this group. Thank you.
Thank you very much for the kind invitation and for the introduction. Let me say a few words about where I'm from. So as Peter said, that is the campus I'm in. So actually my labs are in this building back here. Campus is of the order of, as I said, 10,000 students. We have natural sciences, engineering, so that are the large departments that we have. And you might know Kaiserslautern. I don't know if you have heard the name. Americans sometimes call it K-Town. And in fact, there is Ramstein Air Base, which is just 10 minutes drive from us. And we regularly see the Transall machines landing here over the city, because that's directly the way where they land on Ramstein. So what I'm going to tell you today is done in one of my experiments, the Fermi team. And I would like to point out Alexander. He is the one that gets most of the credit, or has to get most of the credit, for the work I'll present towards the end. And we enjoy collaborations with Michael Fleischauer, Axel Pelster, and Sebastian Eggert from Kaiserslautern, Carlos Sademelo from Georgia Tech, and Giuliano also from University Paris Cité. And of course, we get some money from the German Science Foundation and from the state Rhineland-Palatinate. So what I would like to tell you today is a little introduction about our ultracold world. I want to show you how we can create ultracold quantum gases. And I hope that you are not too familiar with that, because I decided to make a very smooth introduction and spend quite some time on that to show you how our experiments look like and how it all works, that in the end we get these kind of ultracold clouds that have just fractions of 1,000 degrees Celsius above absolute zero. And then I would like to discuss how we can engineer interactions in these gases to make them either form molecules or form many-body states, like those you know from superconducting, conventional superconductors, Bardeen-Cooper-Schrieffer states. And with that in mind, I would like to present some recent results that we had on Floquet engineering of these interactions. And you're not supposed to understand this yet, but what I would like to, in the end, that you all know what we do there and how we can tune interactions basically now at will for these ultracold gases. So let's have a look in the lab and see what we're doing. And let me first explain what I mean by ultracold in this context. So what I show here is a logarithmic scale of temperatures, logarithmic to compress large distances of temperatures. And always in red is our ambient condition, our ambient air. And the blue arrow always indicates where our ultracold gases are located. So what you see here is ambient room temperature is somewhere between the surface temperature of the sun, which is located here, and the point where water freezes. And if we then cool down, what we find very close by on this scale is the point where air or nitrogen becomes liquid. And just a little bit further, that's the point where we can create, or where the coldest fluid emerges, helium, which becomes fluid at 4 Kelvin, and superfluid at 2.7 Kelvin. But you see, what we want to do is we want to go orders of magnitude lower in temperature to bridge an additional 6 or 7 orders of magnitude to come to the point where we create our gases. And of course, you might ask the question, why do we want to become so cold? And the answer is, we would like the atoms or the particles to become so slow. If we translate this temperature scale into a velocity scale, and actually this snail is moving a little bit slower than our gas atoms, then you see if we pick here from ambient air a molecule and just measure its velocity, we would find that on average it has a velocity of a few hundred meters per second, somewhere between a bullet launched here or a race car. If we cool them down, then they become slower and slower. At some point, even humans can be faster than these atoms. And in the end, the velocity will be somewhere between the snail that has now managed to crawl here its way over the picture and, for example, a turtle. And actually, while preparing this talk, I learned that it's the velocity of a turtle at land. In sea, they're an order of magnitude faster, in fact. And that is what we want to have, because now we can see single atoms move and we can study what they do and even see the effect of individual collisions. There is a price to pay, because if you become that cold, of course, any matter would like to form a solid. And in order to avoid this, we have to rarefy the gas. So what is shown here is a similar scale of particle densities, where in ambient air we have particle densities of the order of 10 to the 18, 10 to the 19 particles per cubic centimeter. At the other extreme, there is interstellar space, where we have roughly 1 particle per cubic centimeter. That is here the condition of ultra-high vacuum, where we have 10 to the 5, 10 to the 6 particles per cubic centimeters. And the cold gas is somewhere right in the middle, 10 to the 12 to 10 to the 13 per cubic centimeter, so that the probability to form a molecule and then a solid is so much reduced that on realistically experimental timescales, we just can work with a gas. All right, how does it look in the lab? Of course, you can imagine if we want to go that low in temperature, there is not a standard refrigerator where you can just open, put something in and cool it down to micro and nano Kelvin. What we do instead is we have an ultra-high vacuum system, and that is a picture on our optical table. And admittedly, it's not very tidy. But what you see here is an ultra-high vacuum system where we shield our experiment from any ambient air conditions, because any particle that would hit our ultra-cold gas would deposit a lot of energy. And at the heart of this, just buried below this shielding down here, is an ultra-high vacuum glass cell. And everything that I'll show you takes place in this glass cell. It has superb optical quality and is designed to let laser beams pass through at the right wavelengths. So whatever I'll show you, all the pictures, everything is taken in here. And basically all laser beams in the lab, all the radio frequency and everything is just made that the right pulse comes at the right time in the middle of this glass cell. The technology I'll explain in a second to cool the particles and to trap them, to manipulate them, relies a lot on lasers. So we have a second table, and on this table we have a lot of laser sources here, lots of optical elements. It's not the storage space. We need indeed so many optical elements because light has so many degrees of freedom, and we need to control them all. And that is the intensity, the frequency or color, it's the size of the beam, it's the polarization. This all we want to adjust. And between any of the two adjustments, we have mirrors to steer the beam very precisely. And once we have controlled everything, we couple the light here in these optical glass fibers that you glow here in red. And over the ceiling, we guide the light to, in the end, shine here into the glass cell. Now let's have a look. What could happen? How could you imagine to exert a force to manipulate particles with laser light? If you imagine the atom as a two-level system, and here is a resonant photon approaching, the atom can absorb the photon, and in this absorption process, energy and momentum must be conserved. As a consequence of this momentum conservation, the atom gets a little kick. And this kick is the one that we're interested in. But at the same time, the particle is still excited, the atom here, and it wants to get rid of the energy, so it emits a photon. But the emission process, as indicated here, is isotropic, goes randomly in any direction. And if you average over many of these absorption and re-emission processes, you get a directed momentum kick from the absorptions, but the emission events all average to zero, so you get a net momentum transfer, and via the rate of the photon absorption, you get a net force onto the atoms. And this you can now use to cool if you take this arrangement of counter-propagating beams that are a little bit retituned from the resonance line. So if the particle sits here in the center and is at zero velocity, it sees the laser beams retituned, so there is no scattering. If it moves in one direction, it sees the co-propagating beam even further retituned, so it does not scatter any photons from that. But the counter-propagating beam will be blue detuned by the Doppler shift, so it sees this one tuned into resonance, it starts to scatter photons and sees a force that is opposing its motion. And this leads to a velocity-dependent force, and that is like a friction. And thereby you can cool particles, and if you do it right, you get little gaseous clouds here of the order of 10 to the 9 atoms at 10 to 100 microkelvin, already 10 millionth fractions of a Kelvin above absolute zero. And obviously the atoms like what we do. And this idea dates back to Ted Henge. He got the Nobel Prize later on for the invention of the frequency comb in 2005. And for the realization of laser cooling, there was a Nobel Prize awarded in 1997 to Stephen Chu and Bill Phillips. And in the same year, Claude Cohen-Tanucci got it for his development of dressed states. Now, the scattering force is not the only force that a laser beam can exert. There is a second one that we need in the following, and that is to form a conservative trap without scattering photons. In neutral atoms, you can show that neutral atoms cannot have a permanent dipole moment. But if you had a permanent electric dipole and you brought it into an electric field, then you remember from introductory physics, there is a potential or an interaction energy associated with it that amounts to the product of the dipole moment and the electric field. Even in a neutral atom, you can induce a dipole, and this dipole can be induced by a time-varying electric field, and the size of this dipole is given by the strength of the electric field and the polarizability of the atom, and that depends on the frequency. If you plug it together, and that's a very coarse derivation, and if you want to go into detail, there is a seminal paper here by Rudi Grimm, Matthias Weidemüller, and Oshirnikov. If you plug it together, then you find that there is a dipole potential exerted or created by a laser beam on a neutral atom that depends on the polarizability via the frequency of the laser beam and the intensity of the laser. And this formula essentially is half of the success of the whole field of cold gases. Why is that? The first part tells you that by changing the frequency, you can change the character of the laser trap you have. If you form a focused laser beam or a focus of a laser beam, and you tune your laser a little bit red of the atomic transition, then atoms will be attracted to the intensity maxima, and you have formed a trap, a well. If you just tune your wavelength or the frequency a little bit above the transition frequency, then atoms will be repelled from intensity maxima, and you have formed a potential bump. And in fact, this change of character is exactly what you might know or remember from your introductory physics lecture. If you have a driven harmonic oscillator and you change the driving frequency from below to above the resonance frequency, you calculate and you see a phase shift. And this phase shift of pi is exactly the difference between attraction and repulsion in this formula of the induced dipole moment. So we can form traps and we can form potential bumps. However, we can also now play with this intensity. And whatever we can paint by light can be a potential for the atoms. It doesn't have to be a simple focused laser beam. It can also be, for example, this simple cubic lattice created by interfering several laser beams. And people have played around with this and created two-dimensional potentials that resembled the one potential that you have, for example, in graphene. You can go to quasi-crystals. You can, anything that you would like to study and that you can paint with light can be a potential for a quantum gas. And we use it now because we need to trap the atoms into such a laser trap to prevent them from scattering photons even more at these 10 to 100 microkelvin. And with this, we want to tune now the temperature even lower. And this is done by a very simple method that is called evaporative cooling. And this is essentially what you do every morning if you drink a tea or a coffee. You let the hottest atoms escape, the rest rethermalizes to a lower temperature. Experimentally, what we do is we take here gas at a certain temperature, we cut away the high temperature tail of the Maxwell-Boltzmann distribution, and by collisions, the rest thermalizes again to a new Maxwell-Boltzmann distribution at a lower temperature. We do this very strongly in the sense that we lose many atoms, but the rest creates temperatures of the order of 100 nanokelvin and below. And that is what we will need to form, as I show you in a second, quantum gases that behave quantum mechanically. Just to show you how this works in the lab, let's imagine we zoom now into our vacuum system. Here is a picture that shows you these little needles. So all the rest is unfortunately the laser light that scatters from the walls of the vacuum chamber. But these little needles are ultracold or laser-cooled atoms that shoot here in an atomic beam into this little hole in the vacuum system. And on the other side of the hole, we have our glass cell. The atoms are emitted from this little central hole here, and they are captured here in the center of the glass cell in this laser cooling by 3 pairs of counterpropagating laser beams. And here you see just the reflections of this little cloud of atoms in the surface of the glass cell. The next picture shows exactly the same, now taken by a different imaging method, an absorption imaging that I'll show in a second. This background here is this ultracold cloud. What you see here as beams, that is the dipole traps, or these conservative traps, and where they cross, we have a high density of atoms. Here we can do evaporation to, in the end, create Bose-Einstein condensates, and just this change as we let the Bose-Einstein condensate evolve shows that indeed it's the wave function that we see here expanding. Let me briefly explain how these images come about. It's very simple. We just let the cloud or the Bose-Einstein condensate or whatever we have, we let it drop. It falls under the influence of gravity in a time of flight. And then after a few milliseconds, we illuminate the system by a resonant laser beam. And because it's resonant, light is scattered by the atoms. And on a CCD chip, we capture the shadow that is cast by the cloud. And these are typical pictures that we get. That is a picture of a Bose-Einstein condensate, which is a quantum gas. That's the wave function that we see here, very sharp, where we see how sharp, so to say, the transition is from density to no density. That is a meta wave interference pattern that you might have seen if you do interference with lasers from grating. And it's exactly the same physics that you have here, diffraction orders at 2 h bar k, where k is the momentum of the wave of the optical lattice where it was emitted from. I'll explain this in a little more detail in a second. That here could be a thermal cloud, but in fact it's a so-called mod insulating system, a very correlated state where the details lie in the noise correlations, for example, of this picture. But we can also do Stern-Gerlach type experiments and single out the individual Siemens substates to quantitatively count here spin values or spin populations. So that is where we take our data from. And if we do everything right and cool the system very strongly, we create quantum gases, but now we have to make a very strong distinction between two different types of systems that we can create. In nature, there exist two kinds of particles, and they are distinguished by their so-called spin value. There are particles that have integer spin value of 0, 1, and 2, and there are ones that have half-integer spin value, 1/2, 3/2, and so forth. The integer ones are called bosons. They obey Bose-Einstein statistics. The others are called fermions, and they obey Fermi-Dirac statistics. Bosons might be photons or quasi-particles, like phonons that you know from condensed matter. Fermions are all elementary particles like electrons or nucleons. So if you look at the distribution function, you see the only difference essentially is this -1 or +1 in the denominator. So this first of all tells you when quantum physics comes into play. Whenever this +1 or -1 plays a role, then you're in a quantum regime. If this exponential function is so large, for example, that the -1 or +1 does not play a role, then you can approximate this very easily by a Boltzmann factor, and then you're in classical physics. If this exponential function is small enough that the -1 or +1 plays a role, then you have to deal with this quantum mechanically. The second important thing is this exponential function is positive, but for one value of the energy, and if that matches the chemical potential, this becomes +1, the denominator is 0, and this distribution function diverges. And what that means is this distribution function tells a particle, if the system has temperature T, with what probability will I end up in an energy level E if I go into this ensemble? If the distribution function diverges, the answer is no matter what your energy is, you have to go to the ground state. So there is only one energy level where all the particles have to go, and that is in fact what a Bose-Einstein condensate is, where all particles go to exactly one state, and that is the ground state of the system. And in fact, that is closely related to what happens in a laser, where also all photons are emitted in exactly the same mode. For the fermions, that does not happen. Instead, what happens is that all the fermions fill up the states of a trap up to the Fermi energy. This is indicated here by two different spin values. Spin up indicated as blue, spin down indicated as red. And here the Pauli principle, or the symmetry of the wave function, tells us that no two fermions with the same quantum number can be in the same quantum state. All right. So we can create in the lab essentially both of these situations depending on the question if the particles that we use are bosons or fermions. And for the rest of the talk, I will be talking about a fermionic quantum gas realizing this situation shown here. An ideal Fermi gas filled up to the Fermi energy. And one important consequence of the Pauli principle is that the blue balls, or the spin-up particles, can never interact with each other at ultra-low temperatures, nor can the red ones with each other. The only interaction that is possible is between blue and red. So we have to talk about, for a few minutes, about how we can engineer and understand interactions in an ultra-cold gas. And now, I don't want to lose anybody. The next 2 or 3 slides will have some formula. But in the end, everything will boil down to a very simple description. So if you don't like formulas or if it's too fast, you'll get into the business very quickly in a few slides. So if we want to describe now interactions at ultra-low temperatures, what we have to do in principle is we have to solve the Schrödinger equation, where we plug in as potential the interaction potential between the two particles, and that is complicated. They might interact via a singlet or a triplet potential that can have curvatures and be complicated. So one would like to simplify this a little bit. And in fact, that works because if you had already quantum mechanics and you remember how the hydrogen atom is solved, you can solve for any centrosymmetric potential the radial part of the wave function by the spherical harmonics. And the only thing you have to deal with is the radial part of the Schrödinger equation. If you do that without solving a three-dimensional Schrödinger equation, you only have to solve a one-dimensional, only for the radial part. So there is only R here in the operators and in the potential. The only price you have to pay is that you get a centrifugal barrier, where you have here the angular momentum of the wave function. But now, since we have so cold temperatures, we can easily show, and I don't do that, you have to believe me, that any angular momentum which is non-zero will never be able to penetrate the centrifugal barrier and will be reflected. There will be no interaction by any angular momentum which is larger than zero. And the only thing we have to really consider is the lowest, the zero angular momentum, or the S wave. And doing this, the calculation becomes a little more simple. And doing so, you can show that you only have, or you can describe all the interaction by a single parameter, and that is the scattering cross-section, which depends on one length scale, which is the scattering length. So that's the typical result you get after a page of calculation. And even that is too complicated for us. We want to simplify this even more, because this k that is contained here, this k squared, that parameterizes the energy, and we are so ultra low, we can go to the zero energy limit, where this scattering cross-section is just a very simple term, 4 pi a squared. So if you imagine you're a particle and you cruise through the gas of other peer particles, this tells you that the scattering cross-section, the probability that you scatter, is given by the geometric size of the particle with a fixed length scale or radius a. And this length scale a comes from this quantum mechanical calculation. You can, if you like, forget about this calculation and only imagine that particles have like a hard sphere radius of a. For indistinguishable particles, you have to take into account the symmetry relations, and this you get an additional factor of 2. And there is one very interesting question that you could ask, and that is, if you now could hypothetically tune the scattering length a, this radius, what is the largest scattering cross-section that you can ever have? And if you make a very large here, at some point this +1 is unimportant, then you can cancel the a and you will get the saturation, and that is 4 pi over k squared. And that is a so-called unitary Fermi gas, the most strongly interacting gas that you can have, and we will need this in a second. First, let me show you an experimental evidence that it's really so simple, that it's just S-wave collisions that determine the interaction in the cold gases. And for this, we take a Bose-Einstein condensate, a bosonic quantum gas, and we fill it into this periodic potential. If you now switch off the periodic potential, what you will get is that particles from each potential well will emerge like Huygens elementary wave, like in optics. And in the end, what you will get is, after time of flight, an interference pattern, a matter wave interference pattern. If you make the condensate very dense, then as the particles from the center want to go to the diffraction order, they might collide with another particles, and you see that the colliding particles, they all end up on a sphere, and this scattering sphere is completely symmetric or isotropic and shows you that it can only be S-wave collisions at these ultra-low temperatures that play a role. Now, this S-wave collision determines how strongly the atoms are interacting. And now comes the second half of the big success of the field, that people have understood that this S-wave scattering length, or the size of the particles, can be tuned. So as what I explained is that in principle everything takes place in such a interaction potential, where here in the dashed line that indicates the incoming wave energy that we have. And it turns out that because we have multi-level atoms, there might be other potentials. For example, if this is the triplet potential, that can be a singlet potential or something else, where you have bound states in. You could never come into these bound states because asymptotically the energy is too high. But if for some reason the energy of this bound states comes into resonance to the incoming energy of our interacting particles, and if there is a coupling, then there is a scattering resonance. And the scattering resonance leads to the fact that the S-wave scattering length diverges. It can become extremely large, so the particles become very large and interact very strongly with each other. It can become even negative, and that means the particles attract each other instead of repelling each other, or it can be zero. And that means using such scattering resonances, you can completely tune the interaction properties of quantum gases. And that would be in solid state physics as if you were able to tune the charge of electrons in the conduction band, for example. And for the atoms I would like to present, that is lithium atoms, this crossing of energy levels is shown here. So that's the energy of several levels as a function of magnetic field. So we tune this energy difference here by an external magnetic field. You see the dashed red line is here this threshold, our energy of the incoming waves, and that is tuned because of some magnetic moments of the incoming atoms linearly with magnetic field. And then we have two bound states belonging to two different nuclear levels, I equals 0, so 0 nuclear spin and nuclear spin equal 2. The one is unaffected by magnetic field and crosses this threshold here at a very sharp, large angle. And that gives rise to a very narrow Feshbach resonance where this width is only over a very narrow magnetic field range. The other level here you see is also bending down and cuts just far, far away from here on a very shallow angle. And that shallow angle gives rise to a very famous Feshbach resonance in lithium that is very huge. And the large magnetic field range comes from the fact that this crossing is at a very shallow angle. Now, to quantify this interaction across the Feshbach resonance, let me introduce one parameter. If we take the Fermi energy, and again, if you don't like formulas, just wait a minute, I'll give an intuitive picture in a second. The Fermi energy is just the kinetic energy of the particles at the Fermi edge. And that is if you take the Fermi momentum as kf, it's h bar squared kf squared over 2m. And if you explain or cast this in terms of the particle density, you can find that it's proportional to the particle density to the power of 2/3. If you resolve this for the Fermi momentum, you find that it's the third root of the density. And the density is 1 over distance cubed. So the third root means kf is 1 over density. The Fermi wave vector is a inverse measure of the particle density. The scattering length was a measure of the particle size. And that means if we form the inverse product of kf and a, we have a dimensionless quantity of the interaction strength. If we have a very weakly interacting gas, small particles with large distance, this 1 over kfa is very large compared to 1. If we go to the classically strongest interaction, it is particle size is as large as the distance, then we come to 1 over kfa equal to 1. But quantum mechanically, particles are waves, they can penetrate each other, and this 1 over kfa can even become smaller than 1. And that brings us to a very famous phase diagram of the interacting Fermi gas. We have here on the horizontal line 1 over kfa, and vertically you have temperature. Let's have a look at the 1 over kfa range. If you are in the positive range, there is a bound state below the threshold and particles can form bound molecules. These molecules are bosons and you get a molecular Bose-Einstein condensate if you go below a critical temperature. On the other side, you have all the conditions you need for a Bardeen-Cooper-Schrieffer superfluid, effective attractive interaction in the presence of a Fermi C. And as a consequence, if you go below the critical temperature, you form a BCS superfluid state. And in the middle, if 1 over kfa is 0, you saturate exactly this cross-section at the 4 pi over k squared value. And that's the so-called unitary Fermi gas, where microscopic details don't play a role. And it doesn't matter if you look at an ultra-cold gas of lithium atoms or at the core of a neutron star, for example. The Fermi systems there behave very similarly. Good. So this we can do in the lab. Here are pictures of molecular Bose-Einstein condensate, a unitary Fermi gas, and a BCS superfluid. And in my group, we do all kinds of physics with that, looking at quantum engines, driven diffusion. We look at quantum probes having single particles here and looking what can we learn about the surrounding gas, measuring the single atoms. We look at the interplay of pairing disorder and time dependence to understand better some effects in condensed matter physics. And I would like to now present one recent result in the last few minutes, talking about so-called Floquet engineering of Feshbach resonances. So the Feshbach resonance is what I explained just before. You bring a bound state into resonance and you can tune the scattering length at will, for example, to prepare such a BCS superfluid state. Now, Floquet is a different concept that now brings in time-dependent and periodic modulation. And I would like to introduce this as a comparison to something you might know, and that is the Bloch theorem in condensed matter. In condensed matter physics, you're dealing with periodic potentials. So you have a periodic potential, here a shallow one, here a very strong one, where the potential after a certain periodicity takes on the same value. So if you go one potential further, you have exactly the same value again. So the V of R plus the periodicity is the V of R. The Bloch theorem then tells you that the solutions of this is the product of a periodic function, U, and a phase factor. And the phase factor is given by the wave factor K and the position coordinate R. And that means you become waves that here for weak lattice are sine-like. For a very deep lattice, it can be a periodic function of Gauss-type wave functions. And this phase factor now tells you what is the phase relation in neighboring lattice sites, and it can be the same phase or it can change the phase by pi. And the spatial periodicity is, it just states that the underlying wave function here just reproduces periodically. And as a consequence, you all might remember from condensed matter that you get energy bands that are shown here. So that is in the reduced zone scheme, the energy bands that you have. And if we look, we can identify the different solutions that we have here with different points in our band structure that immediately tells us how the phase relation of different lattice sites works. So that is just a super quick wrap up of Bloch's theorem and energy bands, because now Floquet's theorem is exactly the same, but in time. Instead of a periodic potential in position, you get a periodic Hamiltonian in time. So you have a periodic modulation, for example, at a certain frequency, and after one period, you recover exactly the same Hamiltonian again. Instead of a Bloch theorem, a Bloch state, you get a Floquet state that tells you the solutions to this Hamiltonian are periodic function, time periodic functions that repeat again after exactly the period of the drive. And the relative phase of these functions is given by this factor epsilon alpha, which gives rise to quasi-energy bands. And I would like to very briefly show you from a completely different experiment what effect this has. So in the static case, you have Bloch bands, and I take here from an experiment in condensed matter a measurement of ARPAS, angle resolved photoemission spectroscopy on a semiconductor material. Wherever it's bright, there is electronic density in exactly this band structure. And you see here a certain band emerging in the static case. And now the system is modulated very quickly by a very strong laser pulse. And what you see is that the Floquet, or this modulation, leads to copies of this at higher energy. And these copies, these are exactly the quasi-energy bands that repeat. And depending on the strength of the modulation, these have different strengths, and you can use them now as new energy states in your system. Why do I say this? Because there is a fundamental problem with the Feshbach resonances. The problem is that they're fixed by magnetic field. And if you would like to realize something at a different magnetic field, because there is some interesting physics predicted, the bound state might be very far energetically from your incoming state. And people for a long time, since decades, have thought about how can we realize still a Feshbach resonance here. And the idea was mostly to couple directly by laser beams, microwaves, radio frequencies to bound states and thereby realize this Feshbach resonance. And we go the other way. And I have to say, this is not our idea. It goes back to here some theory papers and also from our department, Christoph Dauer, Sebastian Eggert, and Axel Pelster. They say Floquet modulated and create novel Floquet bands. And whenever one of these Floquet levels match this resonance condition, you have a new Feshbach resonance or a Floquet Feshbach resonance with exactly tunable properties in your system. So the idea is to now modulate the system and to get Floquet, additional Floquet copies of your, for example, here band. And as a consequence, you can then have here a resonance condition that helps you to establish a Feshbach resonance. That is indicated in the example I showed before. Here is the original static resonance lines. And if you now modulate this by Floquet, you get copies in energy space. And whenever one of these copies now cross the threshold, you get a new Floquet resonance. This I show here. That's a measurement of atomic losses because these kind of resonances are unfortunately always accompanied by losses. And wherever there is a loss, it's a Feshbach, Floquet Feshbach resonance. And these A, B, C, D directly correspond to these crossings of the new Floquet bands with a threshold. Down here, that is a coupled channel calculation that's maybe only for the experts, where we precisely to a sub% level can predict where these Feshbach resonances are and what we how we can tune it. And just for those of you who don't know this so well yet, the scattering length can be seen very similar to a refractive index, and this has a real part and an imaginary part. The real part is responsible in the optical case for refraction, in our case for elastic interactions, and the imaginary part is responsible for losses. And in our case, it's two-body losses when the two particles absorb one photon of the drive and got so much energy that they escape from the trap. And now to show you how powerful this method is, what I show here is the resonance position of these Floquet-Feshbach resonances as a function of the modulation frequency. Here for zero frequency, that's the static resonance. There is the small one for the I = 0 nuclear channel. And the broad one that is usually used is very up here at 830 something Gauss. And you see we can induce here Floquet ladders of resonances by by inducing this modulation. And while the I = 2 is linearly scaling, this I = 0 resonance very strongly comes down here into this ladder of Floquet resonance of the low-lying Feshbach resonance. And I want to just flash a few results. So that is more for the experts. That is this ladder of Floquet resonances. We can see here the AC Zeeman shift from the radio frequency drive. And I show this mostly because I want to show the shape of the resonance. So that is here the natural shape of this Floquet-Feshbach resonance that boils down to a line shape which is called Beutler-Fano resonance. And it always appears if you couple a bound state to a continuum. And unfortunately, it points to a very bad disadvantage, and that is the losses. Everything I show here is losses. And this is, of course, bad for us. But the Beutler-Fano resonances have exactly one point here where the losses are 0. And that's an interference phenomenon where all the loss channels interfere destructively. So we were thinking maybe we can use this and tune the losses always to the desired point. And one way we can do is we can not only modulate by one frequency, we can also modulate by the second harmonic. And if we do this, modulate with some basic frequency and the second harmonic, where we change the amplitude and the phase of the second harmonic, we can indeed tune the point where the losses are 0 across the entire elastic scattering, entire Feshbach resonance. So what you see here in dark, that is the elastic channel. And this point where the orange curve touches the zero is the point of zero losses. And it can be here on the repulsive part, but it can equally well be here tuned to the attractive part. And what is shown here in a 2D plot is the losses. What is good is a bright color, the white color, because that is zero losses. And we can tune it here diagonally over the whole range of the Feshbach resonance, and thereby always go to exactly the right point where we want to have elastic collisions. And just very briefly, this we can show, and I don't want to take too much time. What I show here is the static resonance. What we do experimentally is we quench our external trap to induce some shaking oscillations of the cloud. If the interaction is too small, the cloud, so what I show here is the width of the cloud as a function of time, the cloud does not respond. Only if elastic interaction is present, we see like that's a quadrupole oscillation of the cloud with a very well-defined frequency. And what is shown here is the ratio of the amplitude to the damping, which is something like the, how would you call it, the brilliance, the Q factor of this oscillation. And now we go with our Floquet engineering to this point where there is no interaction here, 581 Gauss, induce there the scattering length and tune the loss 0 point always to exactly the magnetic field value that I indicate here. And you see we can tune the elastic scattering length, induce the oscillations as before, while the time that we have before losses kick in is long enough to really see long-lived oscillations. And the quality factor of this is almost the same as before. So we believe we have this Floquet-Feshbach resonances completely under control. And as an outlook, just for the experts, there are so-called bound states in the continuum, that is, states that lie far above in the scattering states, but it is predicted if you're able to interfere two Feshbach resonances, then all the scattering part of the wave functions can be destructively interfered to zero. And if you remember what I showed, there is exactly one crossing of two Feshbach resonances here that we can address by proper modulation. And that is exactly what we do at the moment to realize bound state in the continuum, where we create a bound state which is far above in energy of any bound state in the molecular potential. All right, with that, I've taken up my time. I hope I could show you that ultra-cold quantum gases are ultra-cool. We have lots of tools and methods to control them. And the success of the field is mainly due that we can tune Feshbach resonances and thereby engineer the interactions between atoms in this ultra-cold domain. And by adding modulation, we can even free the Feshbach resonances or the scattering resonances from one position where they are in magnetic field, and thereby, for example, dream about colored superfluidity and so forth. So my group, as Peter said in the beginning, has several projects. This is from my BE-CBCS crossover experiment fermionic system. I have the bosonic system with individual impurities. We work on medical applications for nitrogen vacancy centers and nanodiamonds. We work together with some companies to make this into a surgery instrument. And we have a system where we build together with my colleague Herwig Ott and some colleagues from Hamburg, Klaus Sengstock, Henning Moritz, Peter Schmelcher, a quantum computing demonstrator, Rydberg atoms in individual tweezers that interact via highly excited Rydberg states. And on all these projects, I have PhD students. Therefore, the group is a little larger. And I thank them for a lot of dedicated work. And again, it's Alex who gets the credit for the Floquet-Feshbach resonance. I thank them for their work, and I thank you for your attention.
All right. Thank you, Artur, for this wonderful talk and introduction and fascinating results. I'm sure you've got questions. Right, yeah.
Well, my question is mostly just praise for a very clear talk, and also very inviting, for all of these topics. one thing, since I don't know much about Floquet or Floquet resonances, and another thing I don't know much about is time crystals. So are those concepts connected in any way? Because you had a beautiful derivation, a beautiful analogy there.
Yes, the time crystals are closely related to this Floquet driving. So time crystals in the end is a time analogy to spatial crystals. However, with a difference that the frequency at which the time periodicity occurs in time crystals is an emerging time in the system. In my Floquet engineering, I impose this periodicity by external modulation. And in time crystals, you drive the system, but then there is another frequency emerging in the system. So it spontaneously crystallizes in time. And that's the big difference, the emergence of this time scale. Does that answer your question?
Yes, it does. And so I can sort of think of the analogy broadly as spatial crystallization and crystallization in time. Yeah.
Exactly.
Another question there, yeah.
In the BEC BCS diagram chart, I saw a sort of phase transition from superfluids to the molecular bosonic configuration. So what sort of coupling are you doing? Because I think of superfluids as uncoupled harmonic oscillators.
Let me go back. So this phase diagram, you mean?
Yeah.
So the idea is that if you consider each regime independently and you look on what kind of system do I have, then you get here an interaction that supports a bound state in the molecular potential. It's very shallow below the dissociation threshold, but still, even up here in the normal Bose liquid, two different spin particles, they form a molecule because that's energetically favored. So you have bosonic molecules, and if you cool them further, then you undergo the transition here to a molecular Bose-Einstein condensate. On this side, you have unbound fermions, and if you cross here this threshold or this phase transition, critical temperature, then what happens is that you get fermionic pairing. And the mechanism of this fermionic pairing is exactly the same as in BCS theory, that you form Cooper pairs, and these pairs have a slight binding energy, the superconducting gap, and that lowers the energy of the total system and leads to the fact that you become superfluid because you have the correlations of these spin states on the sphere. So that is in the extreme cases. And let me point out that the superconductors in condensed matter are very, very far out here, where this effective, attractive interaction is very weak. And so this point between -1 and 1, that is now this, what we call the crossover. It's not a phase transition because it's a smooth change. There is no order parameter that is somehow diverging or changing. It's a smooth transition, but it goes, and you see that it's smooth if you look, for example, at the pairing size. Here, the pairing size is very small, it's point-like, and as you go towards the BCS side, it continuously grows until you're here in the typical solid-state BCS pair. So the essential part is that you tune the interaction strength here from one sign of the interaction to the other via the resonance. And it is always, like if you mentioned harmonic oscillators, it's always necessary that two particles interact to have this crossover. Does this answer a little bit your question?
Yeah.
Further questions?
Jose had a question on chat, I can't see, but he asked what atom do you use, which you eventually said was lithium-6, and then he wanted to know what's the purity of the metal. Probably not 100%
yes.
pure.
Interesting question. The purity is 100%. And it's not that we I mean, by the way we do it And let me go back to the very first slide where I showed you the vacuum system. Down here is a lithium reservoir, which has slightly enriched abundance of lithium-6. I think it's 20 to 80%, 20 lithium-6, 80 lithium-7. So this goes out here with natural abundance into the vacuum system. But in this vessel here, when we do laser cooling, the lasers only talk to lithium-6. So it's just impossible that we cool lithium-7 because spectroscopically it's extremely far away. So the lithium-6 is cool, the lithium-7 is not. And then we transport the cold cloud down here. And any room temperature, even heated lithium-7 that we have, or any hydrogen that is remaining in the chamber, that would be like a bomb for the ultracold gas. So that we would see this as a loss of 1 lithium-6 atoms. But what is in the end here in the glass cell that is really 100% purely lithium-6? And if we want to change that, and that is an interesting field that I pursue in the other experiment, is we need to make all the whole effort the completely laser system for a new species to then cool a single or 2 or 3 other atoms of a different element and then merge those 2 systems to study impurity physics. So the purity is extremely high, but if we want to have impurities, we have to really work hard.
Maybe I ask one last question. And while you have the experimental setup shown here, can you speak to the difficulty of modulating the magnetic field at 60 or 40 megahertz? Then probably you need a couple of Gauss. Is this just like a big radio station then, or?
Yes, that is exactly the case. So what you see here is one of the, meanwhile, 4 amplifiers, each giving 100 watts of radio frequency. So what we have to do is to modulate a magnetic field at these high frequencies is like adding a radio frequency parallel to the quantization axis that modulates the magnetic field essentially. If you do this naively, then you fall into many traps. I have a genius PhD student, Alex, and he is not naive, but still he had a hard time because many things you have to learn. There were things that were in the end you could have thought about. So if you modulate at these, using these wires, for example, or having these wires attached close to these high amplitudes, you get surface currents that you need to damp. And these surface currents, if we would look up on the table, there are huge ferrite cores that damp these currents. And that was a major experimental effort to do it. And there is a fun story about it. You see that in the measurement, the data points abruptly stop at about 40 megahertz. And the reason is if we did it at higher frequencies, there were no atoms anymore. And then everybody who's doing experimental physics then thinks, oh, may have radio frequency transition, I kick them out of the trap. You study everything until you notice, wait, why is not even the magneto-optical trap working? And why does my ion gauge suddenly tell me that I have a pressure that is 4 orders of magnitude higher than it should be? And then you quickly panic because you think you have destroyed your experiment. And we found out, and that took us quite some while, that what we do there is some kind of radio frequency baking of the vacuum system. It must be, and we're looking into this experimentally, some kind of radio frequency photo effect. It's a very sharp transition. And then we seem to rip off, I don't know what, something from the walls of the glass cell, and that suddenly increases the pressure. What we then did is we radio frequency baked it in a controlled environment. And then going back, we can go to even higher frequencies, but that was really an endeavor, having these high powers that I did not expect before. And therefore, I emphasize this. Credit to Alexander, he managed it all.
Yeah, amazing work. Well, thank you very much.
It was my pleasure. Thanks for the invitation and have a nice day.